2011 Mississippi River flood was among the largest and most damaging to occur along this waterway in the past century. It rivaled other major floods which occurred in 1927 and again in 1993. To reduce stress on the river levees and control structures during the spring of 2011, the Morganza and Bonnet spillways north of New Orleans were opened. These actions caused flooding in some areas, but were done to prevent catastrophic failure of the levee system and a possible change in the course of the river. This major flood event dramatically increased the flow of water and sediment down the main channel of the Mississippi River and its distributary, the Atchafalaya River. The floodwaters diverted through the spillways could potentially carry tons of sediment into the marshes and swamps of the Delta Plain. Scientists scrambled to study this flood event and to track the movement of sediment carried in the floodwaters. This video follows one group of scientists as they investigate sediment deposition in the wetlands of the Mississippi River Delta Plain. The Mississippi River drains much of the continental U.S., from the Rockies to the Appalachian Mountains. A vast network of tributaries carries water, sediment, and nutrients into the main channel of the river, where it is then funneled to the Gulf of Mexico. Every year the river swells due to spring rains and snowmelt. Before levees were built, floodwaters escaped the confines of the river channel and spread out across the floodplain. The sediment and nutrients in the floodwaters were carried into the marshes and swamps, where they nourished the plants and renewed the land each spring. Water and sediment are the lifeblood of these wetlands. Flooding is catastrophic for human communities, but it's essential to maintain wetlands in a healthy state. The flooding brings in sediment, which drops out of the water as the water flow slows down, and this accumulates on the soil surface and builds the elevation of the soil surface upward. In the 1920s, levees were built along the Mississippi River for flood control, which prevented overbank flooding but starved the wetlands of sediment. The delta has also been subsiding as the river sediment settled and compacted and as sea level rose. Over time, marshes gradually drowned and became open water. From 1932 to 2010, an area the size of the state of Delaware has disappeared. As sea level rise continues, more marshes will disappear without inputs of new sediment to maintain soil elevations. Currently, the river sediment bypasses the wetlands as it is funneled down the main channel and out of the mouth of the river, which can be seen in the satellite image as a dense brown plume mixing with the dark blue waters of the Gulf of Mexico. With the opening of the Morganza Spillway, however, more water and sediment were diverted to the Atchafalaya Basin, where it fed into the swamps and marshes and eventually to the Gulf. The question scientists wanted to answer was how much of this 2011 flood sediment was being deposited in the wetlands. To reach the remote study sites located across the Louisiana coast, scientists use helicopters on fixed floats so that they can land in the marshes to collect samples. I'm standing in a marsh in the middle of a delta that's forming at the mouth of the Atchafalaya River. This is one of two deltas that are being created along the Louisiana coast by sediment that is being siphoned off the Mississippi River by its tributary, the Atchafalaya. The Atchafalaya and the Wax Lake outlet deltas are prominent features that are readily visible from satellite images. These deltas that are located in the Atchafalaya Bay are unique in that they are expanding in size, and their wetlands are more stable than those farther to the east in the Mississippi River Birdsfoot and other basins which are currently deteriorating due to lack of sediment and due to subsidence.
Got 4 centimeters on C, 4 centimeters on the top, and 3 centimeters on chord B. Chord C was also sectioned into 3 separate sections. The top, then the middle 11 because it was real sandy, and then the bottom 2 because it was all organic below that, or it seemed all organic below that sandy layer.
Ah, finally I found that sand.
Oh, that's a good one. So what we are doing here is collecting samples of the surface layer of sediment and measuring the thickness of the deposit. We also save the sample to take back to the lab for further analysis of the sediment characteristics. So how deep was that, the top layer?
In total it was around 11.
Okay. Several centimeters of new sediment were deposited in the freshwater marshes of the Atchafalaya Basin. The presence of plant roots marks the older soil layers. So as these plants get rooted, their roots begin to bind the soil and hold it in place, preventing erosion. The stems also slow the water, and this causes, when the water slows down, this causes sediment particles to drop out of the water and deposit along the banks of this river. Now we're headed east away from the Atchafalaya Basin and toward more saline marshes of the Terrebonne Basin. As we move away from the river, the influence of fresh water will decrease and we may see less sediment from this flood event. These are saline marshes dominated by smooth cordgrass. The salinity here is much higher than in the fresher marshes we just left. As we expected, there appears to be little sediment from the flood reaching these marshes.
One hand push the core down and the other hand hold that. How far down did you go?
We are now headed toward the mouth of the Mississippi River and the extensive freshwater marshes located in the Birdsfoot Delta. The high flow of water from the river here keeps these areas fresh and allows freshwater plant species to colonize. The dominant plant you see here is Roseau Cane. The Mississippi River Birdsfoot Delta, which is located at the terminus of the river, is so named because the shape created by the river channels resembles a bird's foot.
Push it down and pull the piston up at the same time. That'll give us a good core. Come up. And then we'll extrude the core using the piston. The top part, real loose. Many roots in it. So there's a distinct layer ending about right there. And the bottom is just really, really compact. It's not holding much water at all.
What controls marsh stability? When marsh vegetation colonizes a mudflat, the sediment that created the mudflat settles and compacts over time, causing subsidence. The soil surface then sinks and flooding increases. Floodwaters, however, bring in more sediment, which settles out, forming a new layer on the soil surface. Plant roots bind the new sediment and also add organic matter. the soil surface builds upward and thus counterbalances subsidence. So beneath my feet, the ground is slowly sinking, and if I stood here long enough, I would gradually become submerged over time. But if the rate of sedimentation on the soil surface balances the rate of compaction below the surface, then the marsh elevation stays level with the prevailing water level. And with sea level rise, even more sediment will be needed to avoid submergence of coastal wetlands. So now we've completed our survey of the coast and can plot our sampling stations using their GPS coordinates on this map. The different colors of the stations show qualitatively how much sediment was deposited based on our measurements in each location. We can see that more sediment was found near the rivers, especially in the Atchafalaya Basin, and less sediment reached those marshes farthest from the rivers. The information gathered during this survey will help in understanding effects of river flooding on wetlands and also to develop better ways to restore deteriorating wetlands in the Mississippi River Delta.